Hello, Stats class. Here is the beginning of Lesson 6.2 about transforming random variables. And so let's start with reviewing a few things. Remember, a random variable is a variable where the value of that variable depends on chance, which often is stuff we've done before. It's just we're thinking about randomly choosing someone from this population and seeing what their height is or whatever it is. Or sometimes it's rolling a die or flipping coins or something like that. And today we're going to talk about what happens if you do what's called a linear transformation, which I will tell you in a bit why it's called that. But I'll tell you also that linear transformations involve adding, subtracting, multiplying, or dividing by some number. We are not yet going to add two random variables together. That's coming up in 6.2b and c. But for today, we're just going to take one random variable and do something to it by converting it with adding or subtracting a number, multiplying or dividing by a number. And I have a little bit of review for you from way back in Chapter 2, because we did this with data sets, but we didn't do it yet with random variables. And so what we're learning today, we actually have learned before most of the most important concepts. So we learned in Chapter 2 that if you take a data set and you add or subtract something, specifically a number, that's called recentering. And remember we talked about it takes the data set and let's say here's your 3 points and it just slides them over or slides them back, and it does not change the shape or the spread. It only changes the center. And I hope that sounds familiar to you, that you're like, oh yeah, I kind of remember that from back in Chapter 2. It's like a slide in algebra or geometry. So it slides your graph or translates the graph horizontally, and that's all it does. And then we also talked in Chapter 2 about what happens if you multiply or divide by a number, which is also called rescaling. And as you might remember, that if your 3 points are here and you do something like multiply, it stretches them out in addition to sliding them over. So it ends up changing both the center and the spread, but not the shape. If it was skewed right before, it will still be skewed right, and so forth. So that was an important concept back in Chapter 2. Oh, I should add one more thing. In algebra and geometry, these are called dilations or stretches. It stretches the graph or shrinks it, and that changes all measures of center and spread. So that's stuff that we learned when we were working with data sets or samples from a population back in Chapter 2. And now we're going to do the same two things, adding, subtracting, multiplying, dividing, or maybe that's 4 things. We're going to do that same stuff to random variables. So that's not a whole lot different than what we did in Chapter 2. But what we're doing is called a linear transformation. And so these are the linear transformation rules, or the official formulas for this. And this is another situation where anything that shows up in more than one chapter in our book is probably something important. So the fact that it repeats means they really want to make sure you know it. And it's an important concept. So I'm going to use capital letters for my random variables like we've done before. I'm going to say a random variable y is the result of adding and subtracting and multiplying all that to the random variable x. So I'm using lowercase letters for my numbers or constants, and a capital X for the random variable X. So that's kind of a tradition, is that lowercase represents a specific number. In this case, they're constants or just numbers that are being added and multiplied. Y and X are capital because they are random variables. So if you do this, if you take a random variable X, say it's the number that shows up on a die, and you multiply it by something, and then you add it to something, you get a whole new random variable called Y. What happens with the shape, center, and spread in that situation? And before I list those for you, I'm going to point out, take a look at this equation for just a minute and tell me, why is this called a linear transformation? I hope it's really obvious to you from your past experience in math classes. That looks like a linear equation. It looks like a slope and a y-intercept that if you graphed it, it would make a line. And so that's the reason it's called a linear transformation. If you graphed y and x together on a graph, you'd get a straight line. So let's talk about shape, center, and spread. If you multiply and add, the shape doesn't change from either one of these things. And so the shape of y, or the shape of the distribution of y, is the same as the shape of x. We're not changing shapes. And stretching it, even though some students might say that stretching it changes the shape, it doesn't change the type of shape that it is. So the shape, if it was skewed right, is still going to be skewed right. If it was normal, it's still going to be normal. That's what I mean by it doesn't change the shape. So that's shape. Center, well, now we're talking about the mean. So I want to think about what happens to mu y compared to mu x. Mu x is the mean of x. So if I'm adding and multiplying or subtracting or whatever, that changes the center, and this also changes the center. The center changes both by the multiplying and the adding, which means basically this thing that we did to x, we also do it to the mean. If we multiply by b, that multiplies the mean by b. And if we add a, that adds a to the mean. And so it's almost too easy of a formula. It's if every single x value gets multiplied and added, then the mean also gets multiplied and added by those same numbers, or sometimes it would be dividing and subtracting. That's the formula for what happens to the mean of x. And that's basically taking this information and putting it into a formula. It's the same thing we set up above. And then let's talk about spread. This is the one that sometimes gets people confused. We're talking about specifically the standard deviation. And people often think that you should just do the same thing again. You should just multiply the standard deviation by b and add a, and that's no problem, except it doesn't actually work that way if you try it with actual numbers. So let's look at where we wrote spread up here. The adding and subtracting does not change the spread. That plus a thing is not going to be in the spread formula because it doesn't make a difference to the spread of the data. But the multiplying does change the spread. So here's the formula for sigma y. And again, remember y is capital because it's a random variable. What you do is you could ignore the a completely and you can multiply the standard deviation by b. That's the standard deviation of x multiplied by b equals the standard deviation of y. And that's because of what we set up above, that the adding does not change the spread, but the multiplying does change the spread, so we only need this multiplication and not the addition. And then there's one more thing that's a picky detail, and that is, what if b happens to be negative? Well, that could happen. We could multiply everything by a negative. It doesn't happen in a lot of real life situations, and so I don't have a good example of why you would want to do that. But if you did that, for unknown reasons, you can't have a negative standard deviation. So standard deviation of x would be negative. You'd multiply it, or it would be positive, because standard deviation is always positive. You'd multiply it by a negative, and you really shouldn't get a negative. You should get a positive. So the book puts absolute values around this just to say, just in case b is negative, you would have to do the absolute value so that you get a positive result. And then I'd like you to put a big box around this, because this is the main thing we are learning today. So Those are the formulas. They are the same information as what we set up here, except maybe a little bit condensed. In fact, if you like highlighters, you might want to say this is a really important formula right here. And this is a really important formula right here. And the fact that the shape is the same is also important, but I'm not going to highlight it. Those are the two things. All right, so now that we've got that, we really need an example of how this would be used. And what are you going to have to do with this in your homework specifically or on the next quiz? So let's do one of my favorite examples. Let's do Pete's Jeep tours. Pete lives in Africa and runs tours of the savannah to take people out to go look at the zebras and giraffes and elephants and all those things. And he charges quite a bit because, you know, Pete is a smart guy. So he charges $150 per passenger, probably worth it though, to take people out and show them the savannah. All right, that's nice. So what that means is that if you have X is the number of passengers, then the cost would be $150 times the number of passengers. The cost of taking your family out in the Jeep, this is cost, would be 150 times X, which is the number of passengers that were fitting in the Jeep at a time. Now, obviously, it only fits so many people, and so that's another issue, but we'll worry about that later. Right now, I'm going to tell you that the reason these are capital is that they are random variables. So a randomly chosen tour would have X passengers and would cost them this much, which of course is profit for Pete. So the distribution of X is known. So he looks back at his past records and figures out the distribution. Capital X. And we're going to start by reviewing what we did in lesson 6.1b to make sure we've got those formulas. So we'll start with X and probability of X and make our distribution. And we'll practice using the formulas for mean and standard deviation. And I'll tell you that the book does it the very long way. I'm going to do it slightly shorter. Let's say he never takes out only one person at a time. He could have 2 passengers, 3, 4, 5, or 6, and that's how many he can fit in his Jeep. So we'll stop there. And these are the probabilities or the proportions of times that this happens. The most likely thing is it'll be 4 people wanting the tour, but sometimes he has 5, and very rarely he has 6, 5% of the time. We could check that and add up the probabilities and make sure they really add up to 100%, which they do unless I made a mistake somewhere. So let's review the formulas that we learned in 6.1. Let's find the mean of X. And then I'll show you the shortcuts which have to do with the C thing, which we're coming back to. First, we're just focusing on X, just number of passengers. Mean number of passengers on a randomly selected Jeep tour. Well, remember we take the X's times the probabilities and add them all up. So that's what I'm going to do. I'm going to show work thoroughly in case anybody needs that. So I'm going to go ahead and write this all out, even though I probably would pick up my calculator and make it do the work. So you could do this all by hand if you needed to. In fact, you probably could do it in your head if you needed to, or you could type this whole thing in your calculator, or you could do the one variable stats thing that we talked about before. But regardless, if you do all of this, you get the mean, which is 3.75. That's the average number of passengers on a typical Jeep tour that Pete gives. Pete's Jeep is kind of hard to say fast several times. Average number of passengers. We should not round it to 4. Even though 4 is the most common number of passengers, it's the mode, it is not the mean. The mean is slightly less than 4, and we do not want to round because that makes it look like we don't understand what a mean actually is. So there's your mean. And then standard deviation of X. Again, this is the formula we just did in the last lesson. Is a long, big, long square root thing. And we're going to take each of these minus the mean squared times the probability of that happening. I should probably put a parenthesis. And once again, I'm showing work more thoroughly than I normally would because I want it to kind of sink in what these formulas actually are doing. Although this time I'm not going to write out all 5 of these because that's a lot. On the AP test, they are perfectly happy if you write out 2 of them and then put a ... to show that you know that there's more. and then pick up your calculator. That's perfectly legal. Or make the calculator do all of it, but show a little bit to show that you understand the formula. And on the quiz, I'm going to be expecting you to do this and this, or at least two of them with a ... after to show that there's more. So if you do all of this the long way or the short way, it doesn't matter. You still get 1.09, which is the typical deviation from the mean. Sometimes you're about one passenger less than that. Sometimes you're about one passenger more than that. That seems reasonable looking at this table. That's the typical deviation. Okay, so that's the review from 6.1 right there. Let's move on to 6.2. Let's do this. We're going to do something to x, and what we're going to do to it is talk about the cost. So we're going to multiply x by 150, and the book, if you read this book, the example in the book, they do this the long way. And I'm going to talk about the long way, but not do it because it's painful, I have to say, and the shortcut is so much better. The long way would be to take the 2 and multiply it by 150 and get 300. And then 3 times 150 is 750. And 4 times 150, no, I take it back. 3 times 150 is 450. 4 times 150, 5 times 150. Take each of these numbers times 150 and then do these formulas again. And I think they're doing it to prove that what we set up here actually works. I'm going to use the shortcut, honestly. The shortcut is if you take the passengers and convert it to the cost, then your new average also gets multiplied by 150. That is so much easier than what the book did. But I think they're just doing it to prove that it works. If you need that proof, read it in the book or try it on your own. Multiply all these by 150, redo these calculations, see what happens. But I will tell you, it's the same result as if you multiplied this by 150 because multiplying all of these by 150 one at a time is the same as multiplying all of them by 150 afterwards. A little bit of distributive property in the proof for that, which I'm not going to show you. Anyway, this is the average cost per tour, or average profit maybe. All right, based on, depending on how many passengers there are, there'd be an average of 3.75 passengers. This would be the cost if there were 3.75 passengers, which means he's never going to actually make exactly that much. But this is the average out of many, many tours. He's been doing this for a while, so we can consider it a population. Standard deviation. Well, so what I just did is I took this B, which was 150, and I multiplied it by the mean, and I didn't have an A, so I don't have to worry about that. Here's B again. Multiply it by the standard deviation. That's what we're doing. We're multiplying 150 times our standard deviation, which should give us the standard deviation of the cost. Which is fine, we can do that. And I got 163.50. And again, the book did it the long way. They multiplied all of these by 150, and then they found the new mean, which was this, and they subtracted that from each one individually and squared it and multiplied it and square rooted it, and boy, it took a long time. So just say thank you that you don't have to actually do that. This is the typical cost or typical deviation of the cost. But basically, I did both of these with the shortcuts and not the long way. So that's something you can do. If you're multiplying a random variable by a number, you can multiply the mean and you can multiply the standard deviation. In a nutshell, that's what we just learned. And then let's talk about adding or subtracting, because that's the harder part. So let's say for each tour, every time Pete takes a group of people out, he has to buy gas. So let's say he spends $100 on gas every time he does a tour. So now we're talking about, instead of the cost that, or the money he brings in, where they could also be called the income, cost from the passenger's perspective, but income from Pete's perspective. Now we're going to talk about the profit, which is the 150x minus the amount he spends on gas. That's another random variable. Notice now we're multiplying and we're subtracting, so we're going to have to think about those formulas. That's fine. We're going to find the mean of P, which is the mean profit per tour, and the standard deviation of P, which is the typical deviation of the profit per tour. How do you do that? Well, we already did the 150 part, right? So it's C minus 100. If I subtract 100, will that change the mean? Think about that for a minute. Yes, it will take every single value that we just calculated, like all of these times 150, and then subtract 100 for each individual one, which means it also subtracts 150, or 100, I mean, from the mean that we found just a minute ago. So we're going to take this minus 100 and get 462.50. So he doesn't actually get to keep all 562.50 on average. He gets to keep $100 less than that because he has to pay for gas, right? That's my average profit, or Pete's average profit. This is not my small business, it's Pete's, right? Okay. Standard deviation. If I subtract 100 from each individual cost that we just had, and I subtract 100 from all of them, will it change the standard deviation? Think about that for a minute. Think about a dot plot or any kind of graph, and you're subtracting. That slides the whole graph over. It does not change the spread. This is the same spread as that one, because all you have to do is multiply and not add or subtract. So that is what I wanted to make sure you knew, that if you are doing something with adding or subtracting in it, you don't do that part to the standard deviation. You only do it to the mean. So these again are the shortcuts. This one doesn't change because subtracting does not change the mean. And you'll see that in the homework also, and we'll see it a lot more in the next few days because we'll keep using these formulas for other things. But that is it for lesson 6-2A, and we will come back. Just to let you know, Wednesday is one of my favorite activities, and I'm going to make a really awesome Desmos for it. So I'm really excited to be doing ice cream and cake on Wednesday. Look forward to it.